no IRSs and no URS.
Okay. Thank you very much for the invitation. And so this talk is going to be a bit maybe farther from the topic of the conference, but there will be the word random in it. That's the only. So the main difference between all the talks we have seen so far, which many of them were about groups, but in this talk I will also talk about groups, but I will essentially focus on non-discrete groups, so locally compact groups. So let me remind you. During my talk, G will be a locally compact, say, second countable group. And so we just had a talk about invariant random subgroups, but let me recall a little. In any case, so I'm interested in the following space, the space of closed subgroups of G. So the set of all subgroups of G, I take only the closed ones, and it is naturally a topological space. So there's a topology. Let me not tell you what the topology is. I'm just gonna define for you what the convergence is in this space means. So where a sequence of subgroups converges to a given group if the following two things happen. So first of all, you want that for every h in the limit group, there exists a sequence of elements in the converging subgroups which converge to it. So this tells you that you can approximate h with this sequence, but of course there is a second condition which tells you that you cannot do better. So whenever you have a sequence of elements of the converging sequence, such that Hn tends to some limit in G, then G belongs to the limit. Okay. So Ariel already explained it for you, but let me remember. So I defined you a space. And by the way, there is also an action of the group on this space by conjugation. So let me remember that an invariant random subgroup IRS is a G invariant probability measure for this action. Okay, so what are the basic examples of such objects? So first of all, as is clear from the previous talk already, the primary source of example, I mean, the most basic case is just fixed points for this action, which are normal subgroups. Whenever you have a fixed point for a group action, you can consider you have also an invariant measure, which is very boring. It's just the Dirac mass on it. Second example, more interesting. So assume that gamma in G is a lattice. What's a lattice in a locally compact group? What does this mean? It means a discrete subgroup such that when you look at the coset space, this space has a G action and admits an invariant probability measure. Let me call it M gamma. So the basic example of this situation is SL and Z inside SL and R. So already, not that for discrete groups, this is a completely boring notion. It just means subgroups of finite index. But for non-locally compact group, it's very rich. So when you have a lattice, you can build an IRS of your group in the following way. So you can consider the map from the coset space to the space of subgroup, which just look at the stabilizer for the natural actions, which would be the, so to a coset G gamma, you associate its conjugate. It's the stabilizer. And then here you have an invariant measure. You can push it, and you will get an IRS. And this is a big motivation to study IRSs, because in this way, so one of the motivations to study them is that the space of invariant probability measure on a compact space has a topology, as the weak topology. And in this way, you can kind of see lattices as points in this space, which is compact. And then you can use compactness arguments to prove things. There is a very recent proof of Zahid-Gelander of the Kasdan-Margulis theorem, which is based on a very, which is a deep theorem on lattices in simple Lie groups, which is based on a very straightforward compactness argument in this space, for instance. Okay. Third example, which is actually generic. Assume that your space, your group acts on a probability space in a probability measure preserving manner. And then you can also consider a map from the space. So it's, in fact, this is a special case of this, which at every point associate the stabilizer. And you can push forwards the measure, well, I don't know, through this map, and this is going to be an IRS. And in fact, this example is generic, meaning that for every given IRS, you can find an action so that you can realize it this way. Let me write it. So this is due for discrete groups to Aber, Glasner, Yair, Glasner, which is here, and Virag. And for locally compact group, it's written in a paper by 7 authors, known as the 7 Samurai paper. I'm not going to try to list them. Maybe some of them are here. No, I don't think so. There's no, but so I'll try maybe. There is Abert, Bergeron. No, you're not a samurai, no. Gelander, I think. Jan Biringer, Ido Samet, Jean Rambaud, Nick Nikolov, and maybe I'm done. So let's say that every IRS arises as in 3. So actually, I came interested to the question I'm gonna talk about from a different perspective. So I like measure theory a lot, but I also like topological dynamics. And it's well known that there is a rich interplay between measure theory and topological dynamics. Many things that work in one setting, you can try to develop analogs in another setting, and they yield different applications. So that's why in the title there are 2 things written. What is a URS? URS is the purely topological analog of this, where no measure is involved. So formally recurrent subgroup URS is closed minimal G invariant subset. Minimal means that it contains no proper closed G invariant subset, or equivalent is that when you look at the action on this of G, every orbit is going to be dense. Why do we put this condition? This actually is more analogous ergodic IRS than just IRS. So the correct analog of an IRS would be to just ask for a closed G invariant subset in here. However, the reason why we study this object is that somehow the general belief is that subgroups that belong to such objects, or that appear as in this typically in IRSs, behave kind of differently, are more constrained in the general subgroups of a group. And if you don't put any condition, then this is not going to be true, because every subgroup is in a closed invariant subset, just its orbit and close it. But minimality is a big constraint, and this gives you a very non-trivial result on subgroups that appear in this way. So examples, just like before.
Why is it called this way?
Because a point, a subgroup, so a subgroup of this, of G, so a point in this space, belongs to such a set, if and only if it is a uniformly recurrent point in the classical sense of dynamical systems. Okay, and there is kind of a dual. So I'm talking about a subset of sub G, but in fact, what I'm also interested in is its typical elements. I'm gonna pick subgroups in there and try to understand how they look like.
So the current trend is kind of to call sets and points the same way, right?
Huh? Sets. I did not set up this terminology, and I'm happy with it. I think it. So I'm not talking about sets and points in the same way. I'm just emphasizing that this is a space with an action, but it's also a set of subgroups of G, meaning that there are two structures on this space, and it's important to keep both in mind, not to look just at it as a dynamical system. So, which is why.
It's a certain collection of subgroups.
Yes.
You call it a subgroup.
Yeah. Yes. Actually, I'm gonna try to use just this acronym so that it never use it. So that the word subgroup is not going to appear anymore. So what are examples of this thing? So again, normal subgroups. The fixed points are obviously closed minimal invariant subsets. There is an analog of the lattice situation, which is the conjugate, so co-compact subgroups. Okay. More precisely, conjugacy classes of co-compact subgroups. In the measured theoretical setting, the nice notion of kind of cofiniteness is defined in terms of measure. In the topological setting, is defined in terms of topology. And the third example, analogous to the action situation, is slightly more subtle. So I'm going to state it as a fact, which is due to Glasner, I mean, at least in this terminology, and Benji Weiss, Eli Glasner, not the Glasner who's here, his father. But this fact is as follows. If G acts on a compact space minimally, then there exists a unique URS H such that the following holds. All point stabilizer in X, but not all points, such that the stabilizer are going to be in this URS for generic X in X, where generic means in the sense of bare category. So for a comeager set of points, this is going to be true. There is a unique URS. So in the measured theoretical setting, you always consider things up to measure 0, and in the topological setting, very often you consider things up to comeager sets. Yeah. So this now this is gonna be just a compact space on which G acts, and minimal these things that means that every orbit is dense. Yeah, that there's no proper closed invariant subset. Okay, I thought very carefully about how to use these boards, but I already made a mistake. So, yeah, I should have done it before, but now let's just continue like this for now. So it's also true that that this example is generic in this case. This was asked by Gardner and Weiss, and so was proven independently by Gabor for finitely generated groups, and by Todor Tsankov and myself, which is every URS is as in 3. Okay, what am I going to talk about today? So today I'm going to focus on the following questions. So I think it's due to Tsachi Gelander, or at least he advertised this question a lot. And is the following. Is there a space group which has, for which these objects are as few as possible, so those objects. No non-trivial IRS. What do I mean by non-trivial? There are some examples that are always there. So, for example, you have always you have always the Dirac mass in the identity. You also have always the Dirac mass on the whole group G, which are the normal subgroups that are always there, and you have convex combinations of those. So these are the trivial IRS.
So you don't even want a non-trivial normal subgroup?
No, that's very important. No. Such a group should be simple. And then it's also natural, question 2, to ask the same question for URSs. Okay. So these also should have no normal subgroup, no co-compact subgroups, etc. It should be understood as a strong form of simplicity, a dynamical form of simplicity, let's say. So I'm going to give you right away the answer to these questions. No. Okay, this is the way to do it. Okay, this is the way to do it. You have to slide like lexicographically. So the answer is yes. And there are many groups that are known for a long time. I mean, at least that for which this can be deduced from very old results. For instance, PSLNQ has no IRSs. So these are countable discrete groups, and this actually follows from an old result of Kirillov in the 60s. And if you want a group without URSs, take the group of finite, so permutations of n with finite support, which are alternating, even. This has no URSs. And it follows from, so of course Kirillov did not speak about IRSs, but he proved a result which implies this, and in this case also there is a similar situation. So the first reference I found from this fact is due to Segal and Zaleski in the 90s. There's another example that I like a lot. First of all, there's So we were talking with Gadi. Is Gadi here? Yeah, no, he's not. Yeah, so that he was claiming that when you ask to a group theorist a question with probability tending to 1, he's going to answer Tarski monsters. So it's also the case here. So these are some groups, like constructed by Orshansky in the 80s, which have the property that basically they have no subgroups. So this cannot happen because every group must have cyclic subgroup. You take an element inside, it generates cyclic subgroup. But a group such that every proper subgroup is cyclic. So they have no subgroups at all. In particular, they have no uniformly recurrent subgroups and no invariant random subgroups. And another example that I like a lot, and is maybe the more interesting bit in this one, is Thompson's group V, which I will define later. But it's a group defined as a group of homomorphism of a Cantor set. This group has no IRSs, and this was proven by Dutko and Medinets. It does have URSs because it comes with a minimal action which provides a URS of it. It's a simple group, but does have a continuous IRS. However, we proved with Adrian, so I should have told, all what I'm talking about is joint work with Adrian Leboudec. His name was written there. That it has only one URS. So there is an obvious one, and this is the only one. Okay, so why did Saki ask this question? Because the point is that he did not have in mind these examples. So these examples are all discrete countable groups. So this question becomes more interesting if you focus on non-discrete.
But all these examples have an IRS or an URS.
Sorry?
All these examples have at least one IRS or an URS?
No, I'm not claiming this. So actually, I don't even know the answer in. No, what I said is that these are all discrete groups, and now I'm going to focus on the question when the group is not discrete. Sorry, did I get? Sorry. So for instance, here, this has no IRSs. I don't know about the URSs. I would guess it has known, but this has IRSs, but it has no URSs. These have no IRSs nor URSs, and this is what's written. So I mean, it varies. Why should the case of non-discrete group be different? So let me just give you some intuition on some background about that. Or at least more difficult to find examples. So here also, both questions are going to be for non-discrete. So first of all, as was said before, a group with this property should be simple. Okay? And there is something called the Hilbert fifth problem, solution to it at least, due to Montgomery very famous results from the 50s, I think, which tells you the following thing, implies in particular the following thing in the setting of locally compact groups, that a simple locally compact group falls in one of two cases. So either is a Lie group, and in this case, Lie groups always admit IRSs for one of the reasons that I wrote before, because they always admit lattices. So this is a classical result of Borel. And if it's not Lie, then it means, so these are the connected simple locally compact groups. And if this doesn't happen, then it must be very far from being connected. It must be totally disconnected. And there are many classical sources of examples of such groups. For instance, also like algebraic groups, but instead of taking over R, you take them over local fields, so things like this. And these also have lattices, basically for the same reason. They have arithmetic subgroups. And there are also quite different groups, but for example, the group of automorphism of a regular tree. This is a nice locally compact group. Put a plus here because it's not simple. It has an index of subgroups which detects whether you are flipping or not edges. But if you restrict to it, this is a simple group. It's a result of tits. This also has lattices. For instance, free groups are lattice in the automorphism groups of the Kerry graph. There are many closed subgroups of this that also are simple. They all admit lattices, etc., etc., etc. So in a sense, there is a sort of lack of examples in the world of simple locally compact non-discrete groups, and it's kind of a general theme to find examples that are substantially different from the classical one. A lot of the theory that works from like, so I mean, yeah, I think not. So first of all, in order to have a candidate to answer at least the first of the question about IRSs, you should have a simple group which does not have any lattice, which doesn't happen in any of these examples. And such a group was found by Uri, Bader, Pierre-Emmanuel Capras, and Sarah Moses, and Zahi Gelander. Okay, thank you. And it's called the Neretin group. Let me define this group for you. So, what is the Neretin group? So it's related to this example. Take a free regular tree, say. So it has a boundary. And you can look at the group of automorphism of T as a group as acting on the boundary of the tree, which is a Cantor set. And the Neretin group is going to be defined as, I like it to see it this way, the topological full group of this action. So in other words, it's going to be a larger group of homeomorphisms of the boundary of the tree, which no longer acts on the tree, but only on the boundary. And it's defined as the group of homomorphisms that are given piecewise by this group. So such that you can partition the boundary into Klopen subsets, compact open. And you can find elements, honest tree automorphisms, such that H restricted to each of these pieces is equal to the restriction of this. Okay? So it's a larger group. It's a simple group. It was formed by Capujan. It has a nice locally compact topology, which I will define in a minute. And it has no lattice. So the four authors I mentioned, Bader, Capras, Gelander, and Moses, prove that R has no lattice. It's a quite difficult proof, which reduces it to a problem about finite permutation groups, and it's quite technical. So first of all, this is a candidate for the question I was. So now this raises the natural question: what about IRSs? I'm not going to answer this question. So if you came to see the answer to this question, then you're going to be very disappointed by me. But it's not a candidate to answer the second question I asked, because I think it's even more difficult, the question about URSs, because this group acts minimally on a compact space. There is no invariant measure there, but it's still a minimal action, and this action delivers you a URS. So this is typically the difference between URSs and IRSs, that URSs come from and are useful to study boundary actions. All the groups that I mentioned so far come with nice boundaries on which they act that provide non-trivial URSs. So instead, what I'm going to do now is to give you a different construction of groups, which answers both questions simultaneously. But it's going to be so the proof is going to be, it's going to be a cheap construction, meaning that the idea will all be in the definition of the groups, and then the proof will be very, quite straightforward once you had this idea. But the main difference between this group and the group that I'm going to define is that the groups that I'm going to define are not compactly generated, while this group is. And actually, for URSs, I don't even know a candidate of a compactly generated group to answer this question. All locally compactly generated simple groups that I know have URSs. But so first, before I get to define the groups that I want to define, let me. I already mentioned before a group which will play a very important role in this talk, which is Thompson's group V. I promised that I was going to define it later for you, and I will define it now. So what is V? It's a subgroup of the Neretin group that I just defined for you. And it is defined as follows. So in this definition, you have some automorphism of the tree, so it's a group of automorphisms that piecewise given by automorphisms of the tree. And V is the subgroup where all these GIs, so are, let me describe it in words without writing, otherwise it requires a lot of notation. Planar automorphisms. What does this mean? I'm thinking of the three-regular tree as really embedded in the tree. Now, the group of automorphisms, full group of automorphisms, does not need to preserve this embedding. It can just, I mean, you can swap vertices like you want. What I call a planar automorphism is an automorphism which you can write as an isotopy in the plane. So it means that you're just cutting the boundary infinitely many pieces, which correspond to some finite subtrees. And then move these trees around, but without changing locally the order of the branches given by the fixed embedding in the plane that I have. This is Thompson group V, and it's a countable group. Okay? Is it clear? It is dense in here. And I already told you that this group does not have IRSs, because it was proven by Dutko and Manietz. However, this doesn't help to really understand IRSs in the Neretin group. I also already gave you another example in which a similar situation happens. I told you that PSLN Q does not have IRSs, but it's a dense subgroup, for instance, in PSLN R, which does have a lot of lattices. So instead, I'm going to explain a construction which kind of forces, it's also based on this group, but for which we will be able to use the fact that this group has no IRSs in order to prove it for some non-discrete group. I insist in not using these boards. So, yeah. How much time do I have? So, before I make this construction, let me tell you a bit more about totally disconnected groups, because I lied to you in a sense. I defined for you a group. I told you that it has no lattices, it's simple, blah, blah. I told you that it's a locally compact group, but I didn't tell you what is the topology on this group. Okay, so because this group has a very nice topology, it's a group of homomorphism of the Cantor set, so you could put on it the topology that comes from this action, the so-called compact open topology, but it's not going to be a locally compact topology. It's going to be a very bad topology. Instead, sorry, how much time do I have? Is it until 50 or until 5? Or until 5? Okay, that's good. So instead, what you do is, this group contains a copy of the real automorphist group of the tree. So what you do is you take the stabilizer of some points, fix your favorite point in the tree. In the real automorphist group of the tree, this is a compact group. It has a topology, and it's a subgroup of n, and you declare it to be open. When you want to define a group topology, it's enough to define the topology near the identity, because then with the group structure you can transport open sets around. So if you have a subgroup which already has a topology, and then you can try to declare it to be open and see if this happens to be a topology on your group. There is something that you have to check. And the fact that you have to check is the following. So, facts. First of all, yeah, let me say, let G be a group, and K be a compact subgroups, a compact group, which embeds in G. Then you can try to, so this group has a topology, this group has not. Try to define a topology on G by declaring K to be open. And what you have to do to check to do this, so there exists a topology on G such that K is open if and only if K is commensurated. What does it mean? It means that for every G in G, when you conjugate G and you intersect it back with itself, it's going to have finite index. Okay, so this is something that you need to check. And in this case, it's easy to check it because it has to do with the fact that you're cutting finitely many pieces. Like the finitely many pieces is kind of the same as the finite things. But so this gives you a recipe to construct locally compact groups. Okay. It's also true that if you have a totally disconnected group, then it always has a compact open subgroup. This is a classical theorem of Van Dantzig. So this situation is not special. It's always the case that you have a compact open subgroup. And it's also true that compact totally disconnected groups are profinite groups. So you see, they're all inverse limit of finite groups. So they are constructed out of finite groups. So it's kind of a recipe to construct your locally compact groups. Start with your favorite compact totally disconnected group, so profinite, which you construct out of finite groups, and try to embed it into a bigger group in such a way that it is commensurated. But now you see why it's kind of narrow the area where you will find simple groups, because this condition, it's a sort of weak form of normality. So it's going to be trivially satisfied if the group is normal, so if you just don't do anything. But then you're not going to have a simple group. So you have to ensure that it is commensurated without producing normal subgroups. And so it's kind of a trade-off that you have to play. That's so the situations in which this happens in nature are kind of rare, and that's why there is a sort of lack of examples. So here's what I'm gonna do. But I'm gonna follow this recipe. I'm gonna take start from a compact group. My construction will have as input a sequence. So for symmetry, let me index it by z, where the n is a finite group. Any sequence of finite groups. And I will actually realize it as embedded into Thompson group V, which I just defined. Thompson group V contains all finite groups. This is easy to see. You can do permutation groups by swapping equivalent sets around. And now, my group is also going to act on the boundary of a tree, but instead of drawing the boundary like I did before, I'm going to draw the tree like this. Okay, so this is the same three-regular tree, the three-regular tree that I had before. But I chose a specific direction which gives me 2 points in the boundary, which I will call minus infinity and plus infinity. And I will ignore these points. So I will define a group as group of homomorphism of the space that you see here, which is the boundary minus these 2 special points. It's no longer a compact space, it's a locally compact space. And this is exactly why I will not get a compactly generated. But now, so V acts on this, on the tree. So in particular, and I have a lot of flexibility. There is also a copy of V acting on each of these trees that I will denote T0, T1. So my tree is naturally partitioned into these trees. And on each of them, there is a copy of V that acts. And my subgroups, I will realize them as subgroups of homomorphism of this that act here. So, etc. So for each one of these species, which is compact, I have a finite group acting. And now I'm going to define for you this time a locally compact group. So you see that in particular, since I have a finite group on each of these pieces and they have disjoint support, I defined a copy of this compact group here, the product of all my finite groups. It's a nice compact group with the product topology. It lives not in V, but it lives in the group of homomorphism of this space. So this is going to be the K in the recipe here. Now I have to tell you who is G. G is going to be the group of all homomorphisms of X with the following properties.
Because like, V is a stabilizer of point infinity in V. I mean,
So I'm using, I will not be precise because I'm yes. So I have a V. What do you mean? So I have a V which acts on the whole tree. Yes, and I'm restrained to the stabilizer. But then I also have copies of V on each of these three. So you know, I will use freely the self-similarity of V, and I say, yeah, you have a V here. You know. So in particular, the big group is not going to be in V because it's uncountable, but it's going to be in homeo X, and it's locally given by elements of V. And G will also have the same property. So such that. No, if you take it trivial, it's going to be a discrete group. That's the only restriction. So H is going to be the set of all homomorphisms such that for every X in X, there exists an open neighborhood and an element of V. Now V is seen as the whole, homomorphisms, such that they coincide. So this group has this property. It's much easier to visualize than to write down. It's just a group that you want to cut this thing into pieces and move them around by tree automorphisms, where you can do things like this, but infinitely many things like this. And 2, I have these pieces, and I want that, so for every given H preserves the boundary of the N tree, and the restriction of to it belongs to this sequence of finite groups that I defined for all, but maybe finitely many n's. Where the finitely many depends on H. So my group looks like this. An element of my group is take a big chunk of this space, and in there you do V whatever you want, and outside you do whatever you want, but with the constraint that you belong to these groups. Okay? And it's easy to check that this compact group is going to be commensurated, because any given element actually normalizes a finite index subgroup of it, which is the guys outside of this big chunk that I told you. So it is commensurated, and this defines our topology. So the topology is defined by declaring this compact group to be open in there. And as an abstract group, it's a subgroup of the Neretin group, but it's not a closed subgroup. And the theorem, which you might guess by now, G has no non-trivial IRSs, and at the same time no non-trivial URSs. And yes, so why is that? As I said, it's soft construction. So in fact, I already told you why it doesn't have IRSs nor URSs. I just have to translate what I told you to this setting. So how do you understand IRSs? And so first of all, know that as I told you, a totally disconnected group always has a basis at 1, which consists of open subgroups, not just subset, but subgroups. And here there is a very natural one. So set UN to be the product for k in absolute value bigger than n, yeah, of dk for no, n is 1. So this is a sequence of subgroups of this k, which is shrinking to the identity in G. So it is the guys that are in this product and act trivially on a window size -nn. So this is a compact open, and it shrinks to 1 in G. It governs the topology, this sequence of groups. And you also have another sequence of subgroups, which now I cannot. So I'm going to have to raise something crucial, but so Gn, which is the elements of G with the property that they verify this for all things that are at most n. So that the window on which they're able to mess up things is at most n. So such that So this is also a sequence of subgroups. And UN is normal in GN. So yeah, I'm gonna say that. Yeah. So first of all, GN is open. GN increases to G. And UN, as I said, shrinks to G. And UN is actually contained in GN. And it's not only contained, it's a normal subgroup of GN. Okay? And so what's happening here? And the quotient of these two is a famous group in this talk. You can guess what it is. So what is the quotient? So UN, GN is the thing that mess up to scale n, and then do dn. And UN is the thing that do nothing up to scale n, and then do dn. What is the quotient? Is things you understand it just by looking at the action up to scale n. And there you are acting by elements of V, and it's a compact space now. So it's going to be a countable group, and it's in fact it's V for every n. Okay? Now, using this, how do you understand IRSs and URSs of G? You have a natural sequence of maps. Which I'm going to denote lambda n, which go from sub G to itself, that are defined as follows. Take a subgroup here. So the first thing you do is you intersect it with Gn. No, lambda is a map. Maybe I should call it F. I don't know. It's a map from sub G to sub G. Intersect it with Gn. It's a continuous map. Now, it's very tempting to do the following thing. Project it to the quotient. So remember, this is V. So this is something that you don't have the right to do in general. There is no, I mean, there is no such map in general. But here there is one because the subgroups are compact. So typically what could happen is that, I don't know, in R2, if you take a line, which is a subgroup of R2, but it says it's rational slope, you quotient R2 by the integral lattice, you get a torus, and this line is going to be a dense embedded line in the quotient, so it's not even going to be a closed subgroup. But here there is no problem because UN is a closed subgroup. And then come back. So here you take the pre-image. So what you're doing, you're saturating the subgroup with respect to this quotient map. And yeah. And then this is itself a subset of here. So the result is take H and you map it to H, intersect with Gn, and you saturate with respect to Gn. But it's I want to see it like this because of the following reason. Now it's easy to see that, so this map Fn, actually from this formula you see immediately, Un is shrinking to 1 and Gn is increasing to G, which means that when you apply this map to H and you let n tend to infinity, this is going to converge to H. You recover H, and this is the conversion is even going to be uniform. Now assume that you have mu an IRS of G. For the same reason, what's true is that when you take, now you push it with this map, it's not going to be an IRS because here there were non-equivariant steps, but it's going to be a probability measure on the space of subgroups, and this is going to converge it to, you're going to recover the original IRS in weak topology. But what is this thing? So look, here you push. You get something which is no longer an IRS of G, But this map is Gn equivariant, so it's an IRS of Gn. Now you push it to the quotient. And here, this is a group for which you know the IRSs. And so Dutko and Medinet tell us that this must be a convex combination of delta V and delta 1. And then when you go back, you already understood everything, basically. So this is something of the form Tn plus not of the threat entity, but un. But un is tending to 1. So this must tend to something of the form. So yeah. This is the key point here is the result of Dutko and Medinet. Okay, so this is a non-trivial result, but it's true. So that's and so mu is of this form. And what about URSs? For URSs, you can play, roughly speaking, the same game, but there is a minor difference. So I told you that I claim that this group has no URS at all, but I told you that V does have one. So when you go through this step, it's not true that you get something completely trivial. You get, so first of all, so you could lose minimality. Okay, don't bother. You can take a minimal invariant subset inside. But here, you can have a URS. But our result that I quoted with Adriana about the group V tells you that this URS must be either either one of the two trivial ones or one specific URS, which is, so here I'm truncating at n, and here I have this copy of V, which is the stabilizer of a URS that arises from this action, on this chunk. And now, so you do get one URS. But now what happens when n tends to infinity? When n tends to infinity, this URS is going to contain stabilizer of every point. So the difference here is that here the space is compact, but when n tends to infinity, it's no longer going to be compact, which means that the thing that you get is not a URS. Because if you take a stabilizer and you send it to infinity this way, it's going to converge to the whole group G. So even if you fall in this case in this intermediate step, at the end there's going to be no problem because the URS. And yeah, and I'm going to stop here. I'm going to share it. Mm-hmm. No, that's the thing. No, I don't know. So actually, the thing, yeah, I mean, very very likely the Neretin group doesn't have IRSs, but nobody has proven it so far. And for URSs, I don't have in a candidate. And the thing is that we came to this through the URS question. So we kind of we were trying to find a group without URSs. And there we found some example which was in this spirit, but simpler, which was already in the literature and built out of permutation groups. So you play the similar game, but with alt Fn, which I mentioned before. You also can put finite groups or blah. And there, for this group, you can prove basically in the same way that it has no URS, but it does have IRS. But then we figured out if you change a bit, you can also get no IRSs. But yeah, that's it. Mm-hmm. For locally compact groups, the link is not clear. No.
Do you think there might be a chance that it's impossible? Maybe every compact to generate because
You with you or with I?
You.
I am a very skeptical person about groups.
Yeah.
But I really have no clue how to construct even a candidate. All the way to construct compactly generated groups that come to my mind have a boundary. I mean, they're basically so. But I think that more complicated things should exist.
It's not nature; it's the boundary of our understanding.
Exactly. I think so too. I think that the difficulty is basically what I explained before. No, that in totally disconnected groups, you need this subgroup. You need commensuration, but you want also simplicity. And this is kind of a narrow window, and it just happens that in nature this situation is rare. But it doesn't mean that it shouldn't, I mean, like in natural example.